And then he talks about the strong and weak forces. These are less familiar because their strength rapidly diminishes over all but subatomic distance scales. So the strong and weak forces are sort of, they're at play at a different sort of length scale than what we would interact with. So we don't really see them much. In our scales, we more interact with gravitation and with the electromagnetic force. So they're the nuclear forces. This is why these two forces were discovered only much more recently. The strong force is responsible for keeping quarks glued together inside of protons and neutrons. So, you know, the force that's sort of gluing together protons and neutrons, or the quarks really within protons and neutrons, is the strong force. And keeping protons and neutrons tightly crammed together inside atomic nuclei. So that's why sometimes, the force is called gluon, the force particle is called gluon. So it's a strong force, or the strong nuclear force is the name of the force. But the force particle boson that's carrying that force is called a gluon, because they're gluing together the quarks and keeping the nucleus together. So the weak force is best known as the force responsible for the radioactive decay of substances such as uranium and cobalt. During the past century, physicists have found two features common to all these forces. At a microscopic level, all the forces have an associated particle that you can think of as being the smallest packet or bundle of the force. If you fire a laser beam, an electromagnetic ray gun, you're firing a stream of photons, the smallest bundles of the electromagnetic force. So that's how we can think of it. Similarly, the smallest constituents of weak and strong force fields are particles called weak gauge bosons and gluons. The name gluon is particularly descriptive. You can think of gluons as the microscopic ingredient in the strong glue holding the atomic nuclei together. And by 1984, experimenters had definitively established the existence and the detailed properties of these three kinds of force particles recorded in table 1.2. So that's where this table is. I can show you that in just a sec. Physicists believe that the gravitational force also has an associated particle, the graviton, but its existence has yet to be confirmed experimentally. So that's sort of where we understand the electromagnetic force, the strong nuclear force, and the weak nuclear force to some extent, and we even found a sort of theme that unifies them, and we talked about that in the other book as well, in Stephen Hawking's book. But when it comes to unifying these three forces with the gravitation force, gravitation being an extremely commonly encountered and commonly understood type of force, there isn't much luck there. So that's a big gap as well, is that these three types of forces, electromagnetic force, strong and weak nuclear forces, those three and gravitation are sort of not really unified at all by anything. And that's a problem. Basically, we want more unification. We want more understanding of something broadly and something that explains all of this, sort of the theory of everything. These are the four fundamental forces. What's the theory of everything that can bring this all together? Explain to me what is going on, what in the heck is going on with these four forces. And that's the issue that we are not able to address so far without a grand unified theory. But string theory is a candidate that tries to do that, I believe. We'll see. We'll see what Brian Greene says about that. So the second common feature of the forces is that just as mass determines how gravity affects a particle and electric charge determines how the electromagnetic force affects it, particles are endowed with certain amounts of strong charge and weak charge that determine how they're affected by the strong and weak forces. These properties are detailed in the table in the endnotes to this chapter. Okay, let's see, where are the endnotes? Okay, we'll see later. But as with particle masses, beyond the fact that experimental physicists have carefully measured these properties, no one has any explanation of why our universe is composed of these particular